Students, in this video we are going to discuss different tests for convergence and divergence of improper integral of first kind. This is the P test. This is a theorem the integration from a to infinity 1 upon x raised to p dx for x is greater than a and a is greater than 0 converges for p is greater than 1 and diverges for p is less than or equal to 1. Okay. This test is P test. Okay. Now next test is comparison test. Theorem comparison test. Comparison test. Okay. Comparison test is if 0 is less than or equal to f of x is less than or equal to g of x for all x is belongs to closed at a open at infinity interval and if f of x and g of x and f of x and g of x are the Riemann integrals on semi-closed at a semi-open at infinity. Then first if integration from a to infinity g of x dx converges. For converges I will write CGS. Then integration from a to infinity f of x dx converges. Okay. Second is if integration from a to infinity f of x dx diverges. For diverges I will write this. Then integration from a to infinity f of x dx diverges. Okay. See here, students, what is comparison test say? If 0 is less than or equal to f of x is less than or equal to g of x for all x's belongs to this interval. If f of x and g of x are Riemann integrable on this interval. If, see here students, integration from a to infinity g of x dx converges, then integration from a to infinity f of x dx are converges. Second is if integration from a to infinity f of x dx diverges, then integration from a to infinity f of x dx is diverges. Means we obtain convergence and divergence by comparing a function. Okay. We will see examples on this test. First example is show that integration from a to infinity 1 upon e raised to x plus 1 dx converges. Okay. Show that integration from a to infinity 1 upon e raised to x plus 1 dx converges. Okay. Solution: for every x belongs to closed at a open at infinity, we have 1 upon e raised to x plus 1 is less than 1 upon e raised to x. Obviously, means e raised to x is always less than e raised to x plus 1. Okay. And if we take reciprocal of these two, we will get 1 upon e raised to x plus 1 is strictly less than 1 upon e raised to x. Okay. Let f of x, our function f is 1 upon e raised to x plus 1 and g of x is equals to 1 upon e raised to x. Okay. What is comparison test says? If we get f of x is less than or equal to g of x, if this g of x dx, integration from infinity g of x dx is convergent, then integration from a to infinity f of x dx convergent. Here we have to show that this integral is convergent, means we have to show that this g of x is equals to 1 upon e raised to x is, this means we have to show that integral g of x dx is convergent. Okay. So integration from a to infinity g of x dx is equal to integration from a to infinity 1 upon e raised to x dx. Okay. This can be written as integration from a to infinity e raised to minus x dx, and this, therefore integration from a to infinity g of x dx is equal to integration from a to infinity e raised to minus dx is convergent. Why this is convergent? Because in previous video we have seen one note that here alpha is equals to, since alpha is equal to 1 which is greater than 0. That's why this type of integral is convergent. Okay. So by comparison test, we get, here we get f of x is less than or equal to g of x and integral g of x is convergent. Therefore by comparison test, integration from a to infinity f of x dx is convergent. That is integral from a to infinity f of x means what? 1 upon e raised to x plus 1 dx is convergent. Okay. Now we will see next example. Prove that integration from 2 to infinity dx upon under root of x square minus 1 diverges. Okay. Solution. See here students, we have obviously 1 upon root of x square minus 1 is always greater than 1 upon x. Okay. So here let f of x is equals to 1 upon root of x square minus 1 and g of x is equals to 1 upon x. Okay. See here students, we have to show that this integral is divergent. Okay. We have to show that this integral is divergent, means we have to show that this g of x is divergent. Okay. Integration from a 2 to infinity g of x dx is equal to integration from 2 to infinity 1 upon x dx. Okay. And integration from 2 to infinity g of x dx is divergent. Why it is divergent? This is by p test. Because here p is equals to 1. In p test, integral is of the form a to infinity 1 upon x raised to p dx. If p is greater than 1, then our integral is convergent. If p is less than or equal to 1, at that time integral is divergent. Here p is equals to 1, so integration from a to infinity g of x dx is divergent. P test is equal to 1. Okay. Therefore, by comparison test, what we will get? Integration from 2 to infinity f of x dx is equals to integration from 2 to infinity dx upon root of x square minus 1 diverges. Okay. Let us take one more example. Show that integration from a to infinity sin square x upon x square dx is convergent. We have to show that this integral is convergent. Solution: we have no need to write down on hand. For every x belongs to interval closed at a open at infinity, sin square x is less than or equal to 1. Actually, sin x is less than or equal to 1. Why this is? Since mod of sin x is always less than or equal to 1. Okay. And if we square on both sides, what we will get? Mod means root of sin square x. This is root of sin square x is less than or equal to. If I squaring on both sides, I will get square and square root cancel. It remains only sin square x is less than or equal to 1. Okay. Therefore, obviously sin square x upon x square is less than or equal to 1 upon x square. Okay. So let f of x is equal to sin square x upon x square and g of x is equal to 1 upon x square. Okay. Here we will get f of x is less than or equal to g of x. If integral g of x is convergent, then integral sin square x upon x square is convergent. Okay. Integration from a to infinity g of x dx is equal to integration from a to infinity 1 upon x square dx is convergent. Obviously, this is by P test. Because here P is greater than 1. P is equal to 2, which is greater than 1. Okay. Therefore, by comparison test, what happens? Integral from a to infinity sin square x upon x square dx is convergent. Okay. Now, next test is new test for convergence. Let f of x be a Riemann integrable in closed interval AF, where a is greater than 0, which is fixed, and s is greater than a is arbitrary. Okay, means your integral is a is fixed means what? Your integral is from 1 to infinity, 1 to s, like that. Okay. First condition is if there exists a mu greater than 0 such that x raised to mu into f of x is bounded for x is greater than a, then integration from a to infinity f of x dx is convergent. If mu greater than 1 and x raised to mu f of x is bounded for x greater than a, then integration from a to infinity f of x dx convergent. Second condition is if there exists a mu which is less than or equal to 1 such that x raised to mu f of x has a positive lower bound for x greater than a, then integral a to infinity f of x dx diverges to infinity. In case it has a negative lower bound, then integration from a to infinity f of x dx diverges to minus infinity. Here students, write down one note. The mu test above can be put in the following form. Which is easier to apply. Theorem. Let f of x be bounded and integrable in closed interval AS where a is greater than 0 and s is greater than a is arbitrary. Where a is greater than 0 and s is greater than a is arbitrary. First condition is, what is first condition? If there exists a mu which is greater than 1 such that limit x tends to infinity x raised to mu f of x exists, then integration from a to infinity f of x dx converges. Then integration from second case is, if there exists a number mu is which is less than or equal to 1 such that limit x tends to infinity x raised to mu f of x exists and not 0 then integration from a to infinity f of x dx diverges. See here students, this is easy way to apply in problem. Okay, let f of x be bounded and integrable in closed interval AS where a greater than 0 and s is greater than a is arbitrary. If there exists a mu which is greater than 1 such that limit x tends to infinity x raised to mu f of x exists, then we say that integral f of x dx convergent. If there exists a mu which is less than or equal to 1 such that limit x tends to infinity x raised to mu f of x exists but not equals to 0, then integration or integral f of x dx diverges. Okay. Now we will see examples. First example is test for convergence. First, integration from 0 to infinity x square dx upon k square plus x square bracket square. And secondly, integration from 0 to infinity x cube upon k square plus x square bracket square, okay, dx. Here students, we have to test the convergence of these two integrals. Okay. First of all, recall what is mu test says. Mu test says that if mu is greater than 0 and limit x tends to infinity x raised to mu f of x exists, at that time we say that integral to infinity f of x dx is convergent. Okay. If mu is less than or equal to 1, limit x tends to infinity, x raised to mu f of x exists, but this is not equals to 0. At that time we say that integral f of x dx is divergent. Okay. This is the mu test. Okay. When we have to apply mu test, first our aim is to find out mu or to choose mu. Okay. See here students, here bracket square. Okay. So here power of x is this x square. When we expand the bracket, we will get the power of x is 4. Means we will get x raised to 4. And see here students, here power of x is 2. Means if we multiply here x in the numerator by x square, we will get x square into x square is equals to x4. So we will choose mu is equals to 2. Okay. So see solution. First we see here f of x is equals to x square upon in bracket k square plus x square bracket square. Okay. Clearly this function is bounded in interval closed at 0 and open at infinity. Okay. See here students, here we have to choose mu is equals to 2. Why? Because here power of x is 4. Here if we multiply x square, power of x becomes 4. So we will choose mu is equals to 2. Okay. Next, consider limit x tends to infinity, x raised to mu f of x, which is equals to limit x tends to infinity, x raised to mu means x square into f of x. Here f of x is this. So this is x square upon k in bracket k square plus x square bracket square. Okay. Which is equals to limit x tends to infinity, x raised to 4 upon k square plus x square bracket raised to 4. Okay. Sorry, bracket square. This is x raised to 4. So this can be written as x square upon k square plus x square whole bracket square. This is x raised to 4 and this is x k square plus x square whole bracket square. Okay. So limit x tends to infinity, x square upon, if we take x square common, so here in the denominator we will get k square upon x square plus 1. Okay. This is whole bracket square, which is equal to limit x tends to infinity, x square gets cancelled. This remains 1 upon k square upon x square plus 1. If we put here infinity, this k square upon x square becomes 0. So this limit is nothing but 1. Means what? Limit x tends to infinity, x raised to mu f of x is exist, and our mu, which is equals to 2, greater than 1. So we say that by mu test this integral converges. So here we can say that what we can say limit x tends to infinity, x raised to mu f of x is equals to 1, which is finite. Okay. or we can say that here exist and mu is equals to 2, which is greater than 1. Therefore, by mu test, what happened? Integral from 0 to infinity x square upon k square plus x square dx converges. Okay. Now we will solve second example. Here f of x is equals to x cube upon k square plus x square bracket square. Okay. Clearly this function is bounded and integrable on interval 0 infinity. Sorry, a to infinity. Here we have to choose mu is equals to. See here, power of x is 4. Here power of x is 3. If we multiply numerator by x, we will get power of x is 4. So we will choose mu is equals to 1. Okay. Therefore, limit x tends to infinity, x raised to mu into f of x is equals to limit x tends to infinity, x raised to mu means x into x cube upon k square plus x square whole bracket square. Okay. This is nothing but limit x tends to infinity, x raised to 4 upon k square plus x square bracket square. Okay. This is equals to limit x tends to infinity. This can be written as x square upon k square plus x square bracket square. Okay. This is equals to limit x tends to infinity, x square, take x square common, so we will get k square upon x square plus 1. Okay. If we apply here x square, in next step x square gets cancelled, remains only limit x tends to infinity 1 upon k square x square plus 1. And if we apply limit x tends to infinity, this limit is 1. So here limit x tends to infinity, x raised to mu f of x exists, and this one is not equals to and not 0, exists and not 0. So integral, so by mu test, therefore by mu test, what happened? Integral from 0 to infinity x cube upon k square plus x square bracket square dx is divergent. Why divergent? Here mu is equals to 1, and in mu test, if mu is less than or equal to 1 and limit x tends to infinity, x raised to mu f of x exists and not 0, at that time integral is divergent. Okay.